Welcome to today's lesson. Today we are looking at electrochemistry, form 4, chemistry, a question that is very common in any given Kcse examination. And the question we have reads, use the standard electrode potentials for the elements A, B, C, and D given below to answer the questions that follow. The letters do not represent the actual symbols of elements. Initially, we had said, when tackling a question on electrochemistry, we look at the E theta values. Some of them are negatives, some positives, with one having an E theta value of 0.00, and any element that is assigned an E theta value of 0.00 volts is usually hydrogen, and that element is used as a reference electrode, i.e., from there we have negative electrode potentials and positive electrode potentials. We said the guideline should be usually the most positive is the strongest oxidizing agent, and the strongest oxidizing agent will undergo reduction. In other words, oxidizing agents undergo reduction, and reduction always takes place at the cathode, and the cathode is usually placed on the right hand side of the electrochemical cell. So let us go through the questions. The questions we have: part 1, which element is likely to be hydrogen? Give a reason for your answer. You go through the E theta values and identify the one that has an E theta value of 0.00, and that element is element C. The simple reason one can give is that it has an electrode potential of 0.00 volts, hence used as a reference electrode, Roman 2, what is the E theta value of the strongest reducing agent? The strongest reducing agent is the one that is usually more negative. And if you look at all these elements, the one that has the highest negative is element A, with an E theta value of negative 2.90. And the question requires us to write the E theta value of the highest over the strongest reducing agent, and therefore the E theta value will be equal to negative 2.90 volts. We move down to Roman 3. Roman 3, in the space provided, draw a labeled diagram of the electrochemical cell that would be obtained when half cell of element B and D are combined. In this case, let us look at B and also let us look at D. If you look at B, it has an E theta value of negative, meaning it is a reducing agent, and reducing agents undergo oxidation, and oxidation usually takes place at the anode. and the anode is usually placed on the left hand side of the electrochemical cell. We look at D. D has an E theta value of positive 0.34, meaning it is an oxidizing agent, and oxidizing agents undergo reduction. We have already said that reduction occurs at the cathode, which is usually placed on the right hand side of the electrochemical cell. So in this case now, let us draw our electrochemical cell. We have the two containers having the electrolytes. Remember, the two solutions will be connected using a salt bridge. This is the salt bridge connecting the two solutions. We also have electrode. We have the electrodes, but this is the left hand side where we have an electrode of the element undergoing oxidation, and therefore it is element B, meaning this is electrode B and this one is going to be electrode D. The two electrodes are joined or connected through the voltmeter. Then of course we have the two solutions. This is the salt bridge, possibly made up of a nitrate salt, either potassium nitrate or sodium nitrate. And if this is electrode B, this should be a solution of the ion containing 1 molar of B ions. And if this is electrode D, then the solution here, it is the solution containing the ions of D, and it is usually 1 molar D positive ions, which is aqueous. And by so doing, you'd have drawn the electrochemical cell formed when elements B and D are combined. Next, which is Roman 4 of the same question, calculate the E theta value of the electrochemical cell constructed in Roman 3 above. What we know is that to calculate the electromotive force of the cell, or E theta of the cell, we usually take the E theta value of the element undergoing reduction. We subtract the E theta value of the element undergoing oxidation. In this case, the E theta value of the element undergoing reduction is that of D, and D has an E theta value of positive 0.34, whereas that of element B, and that of element B is negative 2.38, that is minus 2.38. Remember, a minus and a minus will give you a positive, and therefore this is like 0.34 plus 2.38 giving us positive 2.72 volts. We move down to part B. During the electrolysis of aqueous copper 2 sulfate using copper electrodes, remember we are electrolyzing copper 2 sulfate using copper electrodes. A current of 0.2 amperes was passed through the cell for 5 hours. Roman 1 part B, write an ionic equation for the reaction that took place. And in this case, you expect copper ions to dissolve. That is, we are having copper which is a solid, copper will dissolve and get into the solution by forming copper 2 ions, and of course this one will need to lose 2 electrons. That is, copper 2 ions aqueous plus 2 electrons. The last one, which is Roman 2, determine the mass of the anode which occurred as a result of electrolysis of copper 2 sulfate. So what we know is that the first thing we need to calculate is the quantity of heat that was passed through copper 2 sulfate, and the quantity of electricity is given by taking the current you multiply by the time. In this case, the current we have is 0.2 amperes. We multiply by the time, which is given as 5 hours, but we have to convert hours into seconds by multiplying by 60 times 60, and this one will give us 3600 coulombs. This is the quantity of electricity that went through the solution. But we know that copper will lose 2 electrons in forming copper 2 ions, and we know 1 electron is the same as 1 Faraday, and 1 Faraday requires 96,500 coulombs of electricity. If copper is losing 2 electrons, it means we have 2 Faradays, and 2 Faradays will be equal to 96,500 coulombs. You multiply by 2, giving us 193,000 coulombs. And we know 193 coulombs is the quantity of electricity required to deposit 1 mole of copper, and 1 mole of copper weighs exactly 63.5 grams. If 193,000 coulombs will be required to deposit 63.5 grams of copper, what about 3,600 coulombs? If you cross multiply, we are going to have 3,600, we multiply by 63.5, everything divided by 193,000, and this one is going to give us 1.1845 grams as the answer to this particular question. Thank you for watching and welcome to this channel. And in case you have not subscribed to the channel, kindly take 1 second and click the subscribe button so that anytime we do a video like this, you'll automatically be notified.